Hello everyone. Today we have the pleasure to present our research contribution on the trade-off between accuracy and interpretability in fraud detection models as the submission number 35. Our team is composed of Nesvijevskaia, Sophie Ouillade, Pauline Guilmin, and Jean-Daniel Zucker. To introduce the problem we address, we will first describe the activities of fraud management. Then we will translate their main practical specificities into performance evaluation of the fraud detection model. Finally, we will discuss how a concrete hybrid approach can provide pragmatic and short-term responses to the needs of banks and policymakers. Let's start by introducing the fraud detection activities. The fraud can be defined as all acts of cheating carried out by deceit and bad faith for the purpose of obtaining an advantage. Fraud induces moral, psychological, and financial damages to individuals, companies, states, or, in our context, the banking industry. Like a hydra, fraudsters adapt and circumvent increasingly sophisticated barriers erected by banking institutions that must quickly take measures to avoid losses while guaranteeing the satisfaction of customers who do not fraud. In this sector, the fraud is internationally recognized as a major and growing operational risk under close surveillance. If IA-based approaches present a true interest for this subject, they face legal, operational, and strategic constraints. However, the fraud management process cannot be reduced to an algorithm. It is an ordinated flow of tasks, each task being tainted by a level of human intervention and by economic issues. Let's discover its operational specificities and their impacts on model performance assessment. The fraud supervision is often declined through the various banking products, by type of operations or channels, and also by fraudsters' finalities. These dimensions are strongly linked to local or national market specificities and trends, such as regulations, competition, or customer behavior patterns in terms of bank product consumption or channel preferences. Beyond such business issues, each type of bank product, operation, channel, and fraudster finality can be characterized by its own data, internal or external to the bank. The fraud detection devices thus face new challenges in terms of operation volume growth and data diversity, especially when fraud dimensions have to be combined to characterize sophisticated and quickly changing fraudulent operation modes. Indeed, fraudsters invent new approaches, test security and prevention barriers, and quickly adapt. In this context, strong and dynamic fraud management is key for the banking industry. A critical issue for a perfect fraud management lifecycle is to mitigate fraud as quickly as possible without slowing down most of the usual operations. Let's describe a typical simplified process in a retail banking industry. As an operation is requested, the first task is to detect a potential fraud. It results in an alert. Most operations, such as cash withdrawals or card payments, are too voluminous to be processed by hand, so the alerting is usually automatically suspending or freeing the operation through a set of fixed business rules. However, the accuracy of these alerts for such rare events is often insufficient. The business filters are too tight, insufficient to stop fraudsters, or too loose, damaging the usual flow of customer operations. For each alert, an investigation is often carried out manually by the back office. The operation is then accepted as quickly as possible, or the suspicion of fraud is justified by explicit arguments. The task is strongly constrained by available human resources. The number of alerts that can be properly controlled is limited, and prioritization is very welcome. Upon a suspicion, action must be taken against the potential fraudster. This third task is carried out by the bank or by the appropriate legal authority in order to quickly avoid or limit the impact of the fraud, such as a financial loss or moral and image prejudice for citizens and for banks. The action can also be needed following the disclosure of a fraud on a transaction that has fallen through the cracks of the previous steps. The action, remaining most of the time manual, has to be ethically and economically justified. Finally, a posteriori analysis is driven in the monitoring task in order to understand the evolution of fraudsters' behavior and fraud management failures. It leads to fraud deterrence and prevention by securing usual operations, for example through regulation or improved authentication, and feeds a process of continuous improvement of previous tasks, fine-tuning the detection model, increasing productivity on the investigation, and enhancing actions against the future fraudsters. The main issue of this monitoring task, usually remaining manual, is to be flexible enough to adjust to bank product consumption and to capture the quickly changing fraud patterns, in particular when these patterns were not detected on time. The global fraud management process represents a cost for the bank, be it through human, technical, or combined resources. This investment has to remain lower than the expected gains, whether it is preserving margins or not losing customers. In financial services, the fraud costs are still quickly growing and the number of manually treated alerts remains complex to understand and too voluminous despite the attempts to optimize business flows with more precise AI-based models. Our major question concerns a pragmatic clarification of the trade-off between predictive and descriptive accuracy faced urgently by banks and policymakers. Should the community learn the most explainable models to support human tasks or the most accurate state-of-art black box models for automatic alerting before using post hoc methods to interpret them? Having clarified our view on fraud process management, we will go further and translate fraud specificities into machine learning performance evaluations and analyze available solutions. The general principle of an AI for detecting frauds is to either detect them because their characteristics differ from non-fraudulent operations, considering frauds as anomalies, or to learn a model of fraudulent operations from examples. Let's detail some key operational issues and associated solutions. The first specificity of fraud is that a vast majority of operations are non-fraudulent. This discrepancy between non-fraudulent and fraudulent operations is a phenomenon called imbalanced data. Because fraud is so rare, datasets will be extremely biased in favor of non-fraud, which can seriously skew the models. The management of imbalanced classes generally requires the adjustment of precision measures and data or algorithm transformation. To illustrate the precision measure problem, let us consider that 3% of the transactions are fraudulent or positive. An algorithm that classifies by default all transactions as negatives, meaning non-fraudulent, will have an accuracy of 97%. It looks awesome, but it doesn't detect a single fraudulent transaction. Thus, the measure to select the best algorithm needs to be adapted. The most common solution is to use confusion matrix. For a closer look at misclassification, different metrics combine the true positive, false positives, and false negatives, ignoring the true negatives component that drowns out fraud information. These metrics are mainly based on precision and recall, but also other metrics respecting the trade-off between both of them. After choosing the right metric to judge the results of the model, we can help the model to better learn how to detect fraudulent operations. Indeed, if the imbalance is too critical, for example less than 1%, classical machine learning algorithms won't succeed to learn correctly. The clue is to give more weight to the minority class, either by modifying the data itself or the algorithm used. The first category of methods is divided into 3 subcategories. On one hand, it is possible to oversample the minority class using random duplication of fraudulent observations or using smooth algorithm. On the other hand, undersampling the majority class can be done in a random way by selecting observations to keep and removing the others, by selecting observations to remove, or by mixing both methods. Finally, hybrid methods can combine both oversampling and undersampling. Algorithm modification solutions can either be based on tree structures or tend to modify the cost allocated to observations, giving more weight to the minority class. It is named cost-sensitive learning, although it is not enough in the fraud context. Let's resume the cost issue. Frauds account for only a small percentage of operations, but the cost of analysis of each alert can be significant, not to mention the customer risk of erroneously suspending normal operations. This leads to using cost-sensitive metrics associating different weights in the confusion matrix. But fraud is trickier. Its cost includes the financial risk of each operation. Indeed, frequent but low-amount frauds, in case of a long-tail distribution, may not be worth analyzing. Moreover, the fraud financial cost can be defined not only by the operation amount, but also by other criteria. Machine learning approaches rarely distinguish costs of the error according to these varying characteristics of the observations, whilst this aspect of misclassification can be critical to avoid drowning the signal of high-impact frauds by the patterns of more frequent low-impact frauds. One of the most pragmatic approaches is to simply exclude from learning phase all operations with low amounts. Considering the cost of fraud is one thing, but identifying a fraud itself can be a challenge. If a supervised model is used, we need to label our examples as fraudulent and not fraudulent. However, some of the operations may be labeled as not fraudulent, although they are. The fraud will be revealed much later, or simply no one will ever know, because the fraud was gone undetected. From a practical point of view, it means that assessing the error of classification will require some attention. When a model makes predictions on a label of unseen operations, it is clear that in our confusion matrix, the confidence in both the true negatives and false positives is much lower than that of the true positives and false negatives. It impacts the performance measure of the associated learning tasks. Anomaly detection is an answer to both imbalanced data issue and poorly labeled phenomena. It is divided into two main categories: semi-supervised and unsupervised approaches. Semi-supervised methods are trained on non-fraudulent observations and then detect abnormal, and therefore potentially fraudulent observations during the test phase. On the other hand, the major part of unsupervised methods are based on nearest neighbors. Finally, some well-known categories of unsupervised methods are also used for anomaly detection, including formal methods using statistical tests or others based on dimension reduction. According to surveys, anomaly or outlier detection was one of the main techniques used in credit card fraud detection in 2004, and it was still the case in 2016. This can be explained by the fact that these algorithms can easily handle not only the lack of trusted labels, but also partly answer to the problem of constant fraud evolution, a so-called concept drift problem. Indeed, to make fraudulent transactions undetectable, fraudsters try to imitate the characteristics and evolution of good customer behavior and constantly test for loopholes in the fraud detection system. For the system, it means that the statistical properties of fraudulent and non-fraudulent operations evolve over a certain time. The concept drift involves a need to retrain the model. Besides anomaly detection described before, other approaches can deal with this problem. Most of the time, the phenomenon is partly captured through manual analysis of operations or model performance. Using supervised models allows the classifier to be continuously updated when new fraudulent operations become available. For gradually drifting environments, such as bank check operations, it is possible then to choose a specific frequency or threshold to retrain the model. It is named offline learning mode. However, in context of risk of abrupt changes or voluminous and velos operations, such as credit card transactions, new stakes arise. Adapt to concept drift, be robust to noise, and able to treat recurring contexts. It is known as stream data, and it involves developing online learning solutions. The easiest way to deal with online learning is to process incremental models. However, these methods require adapting the model for each new example. In order to use less calculation memory and time, several methods propose to work on a window containing the most recent examples, either of fixed or adaptative size. To decide whether to learn the model again or not, we have to detect drifts. A lot of statistical tests consist in comparing the distributions, with recent approaches adapting the size of windows. Afterwards, when the concept was detected, there are several possibilities. Learn against the model on complete historical data or only on new observations, or use an old context model. This subject is at stake as more and more areas requisite to work with streamed data and several fraud detection solutions start to combine online learning and drift detection. Last but not least, interpretability is necessary for many aspects. It allows to create better deterrence and prevention, enables bad actors to accelerate alerts investigation, and justifies action by legal authorities or the bank itself. There are different ways to reach a high descriptive accuracy of the model. Intrinsically interpretable models are generally not accurate enough for tasks such as fraud detection. Some think that we should boost interpretable models to gain accuracy, while others prefer to use state-of-the-art black box models and then apply post hoc interpretability procedures. First, there are model-specific methods. Their main disadvantage is that their use is restricted to a single type of model, and it is therefore complicated to compare performances and explanations of several different models. To counter this disadvantage, model-agnostic methods can be used. They can be global, giving an overall model understanding, or local, such as LIME or SHAP, explaining a particular observation. Most of them go together with very useful visualization tools. There is a real race between making interpretable models more accurate or making black box models explainable. In this presentation, we propose a hybrid approach to get both accuracy and interpretability. We experimentally illustrate the differences between these two approaches under operational constraints in the framework of a European project where two private AR actors had to cooperate to propose innovative solutions for fraud management. This project, called Cerberus, resulted in the deployment of two solutions. First, an anti-fraud software is developed for instant cash transfer fraud, characterized by high operation frequencies and limited human involvement. This software is based on the improvement of a black box scoring model, resulting in a fraud probability score completed with a local interpretative overlay. The second solution is an adaptation of the intrinsic interpretable analysis methods based on the Q-Finder algorithm. This method optimizes business decision rules presented as limited combinations of patterns. It is applied to check fraud management characterized by lower volumes and slower human processes. In the second business context, an operational combination of both rules and scores is implemented to explore the benefit of a hybrid approach. For this model, we take the side of interpretable approach, starting with an optimal combination of rules generated by the Q-Finder. The advantages are that the coverage of the fraud by the rules is generally very good and that the variables that intervene in each rule are co-constructed through feature engineering with the business experts to ensure easy interpretability. This rule generation model is hybridized in a second step with a black box score model developed in parallel on all the operations. This scoring model is intended to be applied after the rules in order to prioritize all the alerts. This prioritization speeds up the work of the fraud experts without deteriorating the intelligible explanation of the fraud. As fraudsters' behavior changes, the rules may no longer be accurate after a certain time. To get around this problem, the black box model is enhanced with online learning. Thus, the addition of a rule based on the score model threshold maintains the efficiency by detecting new fraudsters' behaviors. The majority of the operations in alert will then have an explanation given by the business rules, and others will correspond to new fraud techniques not learned yet by the rules. When the number of alerts not explained by the business rules start to be too high, new optimized rules have to be learned from the recent data. This statistico-economic equilibrium is closely followed as part of the monitoring task. For both approaches, all operations under a certain business-defined amount were excluded in order to maximize financial savings. During all the life cycle, only exceptional frauds would have passed through the radar. These outliers did not appear to be economically pertinent to detect. Let's illustrate our hybrid model with statistical results from a real-world application. We can see that most of the frauds detected each month by a score with a threshold at 50% are also detected by the rules. So the use of interpretable models can be easily privileged for operational reasons. The first, explain alerts by the rules, and then prioritize them with the score. Moreover, the combination of the two models gives better results while adding only a limited number of alerts. Indeed, the available fraud experts cannot handle more than 30 daily alerts. In this example, concept drift did not appear yet, and the last month's frauds are not observed for the moment. The rules are still functional alone. This hybridization is valued as immediately operational and very promising by the first banking partners with significant financial savings. It is being deployed in association with two user interfaces designed for the collaborative investigation and the monitoring tasks. If further model optimizations seem tempting, other considerations appear much more pragmatic, such as fraud perimeter enlargement, automatic link to the bank accountability, or simply data skills transfer to fraud experts. Under investment constraints, these pragmatic considerations remind that the performance of such AI devices are far from being solely statistical. In fraud detection, rule-based approaches remain the standard, but data-based rule learning approaches get much better performance. Furthermore, some tasks of the fraud management can be optimized with black box models, excluding the action legitimation. While the question of which approach will give the best answer is still open, we showed on a practical example that it is possible in the meantime to hybridize both approaches to give short-term responses to the needs of banks and policymakers, driven by economical and ethical stakes, without swallowing them up in a technological race. Indeed, humans are in the loop of many business processes. Predicting a risk is only one step in a more complex environment. Algorithm comparisons only on their performance or explanatory power appear too poor taken outside of the use by the practitioner. Thank you for your attention.